Somewhere nearly a million miles from Earth, a machine with a mirror larger than a tennis court is looking deep into the universe and seeing things that are forcing scientists to rethink some of their oldest assumptions. It is not simply finding distant stars and beautiful galaxies. James Webb is looking back toward the earliest chapters of cosmic history, examining worlds hundreds or even thousands of light years away, and revealing details about planets, galaxies, atmospheres, and cosmic structures that previous telescopes could barely detect. When the first major Webb observations began arriving, astronomers quickly realized that this telescope was going to change the way we see the universe. The James Webb Space Telescope was never designed to replace Hubble. It was built to see a different universe. Webb operates around the second Lagrange point, roughly 1.5 million kilometers from Earth. From there, it can maintain a stable position relative to Earth and the Sun while keeping its enormous sunshield between its instruments and the intense heat and light coming from our star. Its primary mirror stretches about 6.5 meters across and is made from 18 hexagonal segments coated with an extremely thin layer of gold. That gold is not decoration. Webb is primarily an infrared telescope, and infrared light allows it to see through enormous clouds of dust that can hide stars and planetary systems from visible light telescopes. But there is another reason infrared astronomy is so powerful. Light has a speed limit. When you look at something 1 billion light years away, you're seeing light that began its journey roughly 1 billion years ago. When Webb observes an extremely distant galaxy, it is therefore looking at an ancient version of that galaxy. The farther away Webb can see, the farther back into cosmic history it can investigate. And that is where some of the most fascinating discoveries begin. For decades, astronomers developed increasingly sophisticated models describing how the early universe evolved. After the Big Bang, the universe was extremely hot and dense. As it expanded and cooled, matter began gathering under gravity. Eventually, the first stars formed, followed by larger structures and eventually galaxies. The general expectation was that mature galaxies would require considerable time to develop. Then Webb began finding surprisingly bright and massive galaxies at very early cosmic ages. Some appeared far more developed than astronomers initially expected. These discoveries quickly became known in popular science as the impossible galaxies, but the reality is more interesting than the name suggests. Webb did not prove that the standard model of cosmology was completely wrong. Instead, it exposed places where our assumptions about early galaxy formation may have been too simple. Some of these galaxies may have formed stars with extraordinary efficiency. Others may contain more massive stellar populations than expected. Dust, stellar evolution, galaxy mass estimates, and even the way astronomers interpret distant light can all influence what we think we are seeing. Researchers have also considered whether early galaxies assembled their mass much faster than previous simulations predicted. The important point is that Webb has forced astronomers to investigate why the early universe appears capable of producing complex structures so quickly. And the more Webb observes, the more complicated the picture becomes. Astronomers have also observed interactions and mergers involving multiple galaxies at surprisingly early stages of cosmic history. One particularly fascinating example involves several galaxies interacting when the universe was less than 1 billion years old. Imagine the universe at that time. It was still incredibly young compared with today, yet galaxies were already gathering, interacting, exchanging gas, and triggering bursts of star formation. These observations show that the early universe was not necessarily the quiet, simple place we might imagine. It was already dynamic. Gravity was pulling structures together. Galaxies were colliding. Gas was collapsing. Stars were forming at extraordinary rates. And every new observation gives scientists another piece of the puzzle. But Webb's story is not limited to galaxies billions of light years away. It is also changing what we know about planets. One of the most closely watched examples is K218b, a planet orbiting a red dwarf roughly 120 light-years from Earth. The planet is larger than Earth and lies in a region where temperatures could potentially allow liquid water under suitable atmospheric conditions. Webb has examined the light passing through its atmosphere and detected molecules including methane and carbon dioxide. Those detections are fascinating because atmospheric chemistry can tell scientists a great deal about a distant planet. There has also been intense interest in possible detections of dimethyl sulfide, a molecule associated with biological activity on Earth. But this is where scientific caution becomes extremely important. A possible biosignature is not the same thing as discovering life. A chemical molecule can potentially be produced through processes that scientists have not yet identified or fully understood. That is why researchers need repeated observations, independent analysis, and stronger statistical evidence before claiming that life has been detected. The exciting part is not that Webb has already discovered aliens. It has not. The exciting part is that Webb has shown us that it is possible to investigate the atmospheric chemistry of distant sub-Neptune-sized worlds in extraordinary detail. And if future observations confirm an unusual combination of gases that cannot be explained by known non-biological processes, the implications would be enormous. That is why K218b remains such an important target. At a distance of roughly 120 light-years, the light Webb receives today left the planet more than a century ago. We are literally observing an ancient snapshot of that world. Whatever is happening there right now, we will not see it directly for another 120 years. And that strange delay is one of the most remarkable facts about astronomy. When we look into space, we are never seeing the universe exactly as it is at this moment. We are seeing its history. Webb has also demonstrated that distant planets can hide in environments that are incredibly difficult to observe. One famous example is the Beta Pictoris system, a young planetary system surrounded by a large disk of dust and debris. Astronomers have studied this system for decades, but the enormous amount of material surrounding the star makes observations challenging. Webb's infrared instruments provide a new way to study the system and investigate planets and their atmospheres. This matters because planetary systems are messy places. Dust, debris, bright starlight, and overlapping signals can make faint planets extremely difficult to detect. But Webb can analyze infrared light and search for the chemical fingerprints of molecules in planetary atmospheres. That opens a completely different window into distant worlds. Instead of simply asking whether a planet exists, astronomers can begin asking what its atmosphere contains, how hot it is, how its chemistry changes, and what that might reveal about how the planet formed. And then there are planets so extreme that they almost seem fictional. Some hot Jupiters orbit their stars in only a few days. Their daysides can reach temperatures hot enough for rocks and minerals to exist as vapor. Under those conditions, clouds do not necessarily consist of water. They can involve silicate minerals and other substances that would be solid rocks under conditions familiar to us. As atmospheric material moves around the planet, temperatures can change dramatically. Minerals can vaporize on the hotter side and condense as the atmosphere becomes cooler. The result is weather unlike anything found on Earth. There are also worlds where the transition between day and night creates completely different atmospheric conditions. These observations are giving astronomers something they never had before: detailed information about weather and chemistry on planets orbiting other stars. Before Webb, many of these atmospheric processes existed mostly inside computer simulations.